Hey YouTube, it's Roman. Welcome back to Math Monday. Looks like you caught me in the middle of a move. I'm in an art studio right now. Check out some of my pieces. I got a nice abstract one here. I got a nice geometric there. But nevertheless, I got my old audio set up. You're gonna have to bear with me for this week. By next week, we should have everything back to normal, and I'll be in a nice new office setup. So, nevertheless, this week we are going to be checking out the time value of money and the idea of a general formula to apply interest and compound interest over time. All right, so crash course, time value of money. What is it? Well, money today is not worth the same as money in the future. In other words, if you can get money sooner, it's better. Obviously, I probably don't have to be the one to tell you that. But we can think of the time value of money very simply as if we have this timeline where t0, so this is going to be time, t0 is today and cap t is sometime in the future, we can just think of time as money. There's no other way to put it. But we can invest money today at a risk-free rate of interest and assume a risk-free rate of return by some point in the future. So, just for example, if we have $100 today, then if we have some risk-free rate of return, let's just call it, say, maybe 4%, then maybe that's 4% annually. If cap t is equal to 1, then at cap t, if we were to invest this $100 at a risk-free rate of interest, we would be at $104 that 1 year in the future. So in other words, if somebody said, hey, I can give you either $100 now or $100 in the future, maybe 1 year in the future, then very clearly you would want the $100 now so that you could assume this $4 return on the risk-free rate of interest. Moreover, if somebody offered you $103 or maybe $102 1 year into the future, or $100 today, and you knew about this risk-free rate, then you would know that $100 today is more valuable because you can receive that $4 return rather than the $103 or $102 in the future, which would be less than this value 104. Like most things, there is a more general way to write the equation to determine how much interest you are accruing on your principal or the net value of your investment at the end of its horizon. And what I mean by that is we can essentially just compile this into a closed form solution for the amount that your investment is worth at the end of its life. So if we have a principal amount, P, and we multiply it by 1 plus the rate of interest divided by the compound frequency, which we'll talk about in a second, and we raise this to the compound frequency times the total number of time periods, this will be equal to the realized value of our investment. So in this case, if we have P is equal to 100, then A is going to be equal to 104, and we get that by just doing 100 times 1 plus 0.04 divided by 1 raised to the 1 times 1, and this is equal to 104. So that's how we end up with this 104 in our first example where we go over the time value of money. But in general, this can be applied to more complicated instruments that exhibit a compounding frequency. Now, this idea of a compounding frequency is actually quite easy. We're essentially just earning interest on our interest within the same investment horizon. So if we have, say, a 1 year investment horizon, so capital T is equal to 1, and we had two compounding periods, so a compound frequency of 2, then we would earn interest on that interest. So we would earn interest once and then interest on that interest again, hence compound interest. Analytically, what this would look like is we would have $100 times 1 plus 0.04 divided by 2, where we have two compounding periods throughout the life of this particular investment. And we are going to raise this to the 2 times 1, where once again 2 is the compound frequency and 1 is the investment horizon. Now, if we compute this value, we will find that this is actually going to be equal to 104.04. And as it turns out, as M increases, so does A. So the more compound periods that we have, the higher the value of our accrued interest is going to be. So essentially, this is A for when M is equal to 2 and R is equal to 4% and capital T is equal to 1. But all else equal, should we fix the values of R and cap T, if M increases, then A is also going to increase. This goes and begs an interesting question. How much can we increase M by? How many compound periods, how large of a compound frequency can we have given a particular investment horizon? Well, as it turns out, we can have an infinite number of compound periods within one particular investment horizon. What would this look like? Well, it would be A is equal to the limit as M approaches infinity of P times 1 plus R divided by M raised to the mt. And this is actually an interesting equation. And the reason that this is an interesting equation is because it is actually bounded, meaning as we let m go to infinity, we're not going to end up with an infinite value. We're going to actually end up with what's called the continuously compounded rate of interest. And I think that is a great video and a great proof to walk through in the next Math Monday. That's going to do it for this Math Monday, a quick review of the time value of money and a general formula for compound interest. I hope you enjoyed. As I said, in the future, we're going to be back to the original setup, back to the original audio. So thank you for bearing with me this week. Be sure to check out Quant Guild. We just launched our first course, Introduction to Python. Use code SUMMER2022 to get $50 off. We are currently developing our course on machine learning and artificial intelligence, so stay tuned for that. Otherwise, once again, thank you so much for watching, and I will see you in the next video.